Now this film is the last in the series of those on simple harmonic motion. This time for the topic we're going to look at forced oscillations. And that means you are trying to drive an oscillation. Let me describe what I mean. Before, in the previous video, we talked about free oscillations. And with a free oscillation, we were talking about something was set into motion without an external force. I'll just do F external. But this time we're going to deal with forced oscillations, which in effect talk about when we have a sinusoidal driving force when a sinusoidal driving force is applied to an oscillatory system. Good. So let me try and give you context of what that is via a video. So I'm just going to upload this video quickly, and we're going to talk a bit about something which you've all done before, which is pushing somebody on a swing. Because this really captures the heart of those two definitions. Let me just move this out of the way a bit. We want to keep those descriptors in mind, and we're going to play this video. So here we go. Take a look at what's happening in this video. What we have is this is a free oscillation being shown now. It means that somebody's been pushed and they're allowing to swing back and forth. This, on the other hand, is a forced oscillation. Somebody's continuing to push the person, and that person is therefore starting to move with a considerable amplitude. Remember, in the previous, let me just scroll back a bit, what you were looking to do when you push someone on the swing is to get them going higher and higher, increasing their amplitude. And that's what you do by catching them at the moment they come back towards you and they're moving away. However, this is an extreme example of what happens if you start pushing them not when they're coming back to you, but too early. So we'll just take a look at this. This is again, push them, and then you're pushing them again, or missing them, and then pushing them a different time. The amplitude's not there. And similarly, what happens if you push them, but then you push again when they're not with you? It's all about the timing. And that is the key to how to get a large amplitude. So it's about the timing. If you get the timing right, you can get a large amplitude. Okay, so the timing's about the amplitude. Now, when I say timing is a bit of a loose term to use. What we're going to talk about in the future is the frequency. And the frequency in this instance, of course, is how often you're pushing per second. That obviously will correlate with how often this person's coming back and forth per second. So ideally what we're looking for, if you have a natural frequency of a free oscillation, then the forced oscillation must equal the natural frequency in order for you to get a large amplitude. I hope that makes some sort of intuitive sense to you. The natural frequency must be the set which is defined by the free oscillation, which in this case is defined by the length, and g, because it's pendulum motion. That if the forcing oscillation matches the natural frequency, then you get a large amplitude. Okay, so what I wanted to try and show you to start with is give you a sort of an intuitive sense of what we're talking about. But let me load up another video which give us a really, really defined sense of what's going on. So this is another, I should say that the previous one was from Salford University, the previous video. It's an excellent video and one that I've used at a website I've used in the past in previous videos that I've done. So here is the FET animation, which will take us through in more detail exactly what's going on. Let me just draw some attention to what we've got going on here. We've got 4 different systems. In each system we have the mass shown, which I can control, and the spring constant, which is K. I have a damping constant here I can control. I haven't done much with that at the moment, but the big equation I want you to bear in mind here, of course, is that the frequency of any free oscillator in a system which is a mass on a spring, ignoring gravity, is 1 over 2 pi root k over m. So I've set up 4 different spring and masses along here, and we can in turn work out the natural frequency of free oscillation of each of these. So let me just go through each of them in turn. So to start with, we have, there we go, 2.5 and 100 for the first mass. So 100 and 2.5. The second one is 150 and 1.6. That's how it moves naturally. The third one is 4 kilograms and 236 Newton meters as spring constant. And the last one, there's 2.5 kilograms and 452 Newton meters as spring constant. Now, what I'm going to do is I'm going to set, I've turned it on at 0.5 hertz, and I'm going to change those frequencies. What I hope to do is show you that when it's at 1 hertz, I'm getting a large amplitude in this one. When I move it to 1.22 hertz, now I've got a large amplitude in number 3, not so much in number 1. All of them moving slightly, but we've got a large amplitude. When I moved it to 1.54, I've now got the biggest amplitude in number 2. And finally, when I turn it to, what have we got last one, 2.14, suddenly I've got a large amplitude in number 4 and not the others. We call these a resonant frequencies. So all of these have a resonance. Or resonance is taking place when the natural frequency equals the forced frequency. I'm also showing here what happens when I've got a very high frequency. Well, nothing happens in terms of the amplitude at all. And when I've got a very low frequency, they all moved with the same amplitude that the plate's moving with. Okay, wonderful. So what we're going to do is we're going to take it through, I'm going to take you through those bits again, and we're going to see why it was that each of those resonated at the point that they did. I'm going to make use of this equation here, and I'm going to work out the 4 frequencies of each of them. Now, I think I said that we had mass 1. Let me write them down here. So number 1 had a mass of, I'm just going to look these up again to remind myself. Number 1 had a mass of 2.5 and a spring constant of 100. So the frequency, natural for number 1, is going to be 1 over 2 pi square root 100 was the spring constant over 2.5 kilograms. And that's going to give me 1 hertz. For the second one, F nat 2, that gave me, yep, I think that's 1 over 2 pi. We had a spring constant of, I'm pretty sure it's this one, 150, and 1.6 was the mass. That gives me a 1.54 hertz. For number 3, f natural 3, 1 over 2 pi, I had 236 as my spin constant, 4 kilograms of mass, and they give me 1.22 hertz. And finally, for number 4, I had 1 over 2 pi root 452 spring constant newton meters over 2.5 kilograms, giving me 2.14 hertz. So you can do that for yourselves. Bolt those numbers in to make sure they work, and then appreciate that when the forced frequency equals the natural frequency, then we have a large amplitude. And that is called resonance. Okay. Let me see if I can get that running one more time, so we can take a look at it and just appreciate that. Take a look again. Going to make it a bit smaller this time. So my 1.2, so the second one, 1.6, 0.5, that's my second one, so 1.54 hertz that it's moving at. The third one was 4 and 2.36, so it should be resonating at natural frequency of 1.22 hertz. And number 4, 2.5 and 4.52, giving me a frequency of 2.14 hertz. I've turned it on, and you'll notice that our frequency, our driving frequency of our driver is not equal to any of them. So they move up and down with the amplitude of that which the plate moves at. Now I've hit my 1 hertz frequency, and this is hitting a resonance. I'm getting a large amplitude. I'm going to take that to 1.22, and hopefully the third one starts to hit a resonance, which it does. Then I'll take it to 1.54, and we notice now the second one hits resonance. All of them have got a little bit of amplitude moving around, but the resonant amplitude is the very large one. And then finally I take it to 2.14, and the others have a small amplitude, but the fourth one is resonating. And then I'll take this right down and look at what happens when it's at 0.25. So it's very slow. All of the masses have the same amplitude as the driving amplitude. But if we take it incredibly high, the amplitude of all the masses is 0, even though we have an amplitude of the driver. Those are interesting points to note, ready for the next part. So, let me load up the next picture, which you need to be able to sketch and understand, that being the resonance curve. We've got here our amplitude and our frequency. And here, at the moment, is our natural frequency. So at our natural frequency, we've got a large amplitude. And on either side of that, we don't have a large amplitude. In actual fact, to be technically correct, this should probably start from somewhere like that. Because remember I said, so when f is very much less than f0, the forced frequency, the amplitude equals the amplitude of the forced. Or in other words, we could say that the amplitude and phase of the oscillation the same as the driving oscillator. Okay, but if we were to change it slightly and describe what happens at F is very much greater than F0, the natural frequency, then the amplitude tends to 0, as we saw in the previous video. So the amplitude is very small, and the phase is actually, though you might not see it, 180 degrees or pi out. It's really difficult to see. And of course, finally, when F of the forced oscillation approximately equals the natural frequency, then the amplitude is large. And the phase is pi over 2, or 90-degree lead. So you lead by 90 degrees, or pi by 2. Okay, those examples needed to know. Interesting, what's the next interesting bit to know is that when you're damping, then you'll never get as much of an amplitude because the energy is being lost to the surroundings. That in turn does create a change in the natural frequencies. Very minor, worth noting. There is a slight change in the natural frequency of the system if we've got more or less damping on it. But you have a broadening of this peak. So there's a wider response time, whereas here it's a very narrow response frequency. Sorry, a wider response frequency. And yeah, and the next one will look even, let me just sketch the next one in, will look even more broad. More damping again. Wonderful. So the last thing we want to capture, if this graph has captured all of these, if this graph has captured these points talking about the amplitudes, what has captured the phases? Well, that's one other graph that I want to just introduce to us. Though I'm not technically sure they're going to question you too much about this, but I'd like you to be able to see and appreciate what that is. We said without when F naught, the natural frequency, is approximately F, the forced frequency, then we have a resonance. And also the lag at that point is pi by 2. If F is very much greater, oops, let me draw those again, that's a bit poor, very much greater than F naught, then you get a phase change of pi, whereas if F is very much less than F naught, you get 0 phase change. Now that is captured with this. So if this is frequency and phase difference, when your natural frequency equals your driving frequency, i.e. the resonance, your pi over 2 lead on that. Whereas when you're much greater, you're out by nearing pi, and when you're much less, it tends to 0. And the difference between these are the damping. Not very damped, more damped, very damped. You can see the changes in those. Okay, so the rest of this topic is very much talking about examples and how you're going to deal with, mechanically, of course, sometimes resonances are good, other times resonances are bad, but I'll let you look more closely at specifics in the textbooks to get a knowledge on that. Okay, that's it.